Okay, good evening everybody. Today is our 11th lecture. So today I will be solving assignment number 9 and assignment number 10. So I think I have started the recording. Yes, I have started the recording and welcome back Patlekha and Shivam. Let's go to full screen mode. Nice. Okay. So yeah, one information I want to share with you that tomorrow I will also be having class at the same time, 4 to 6 p.m. Okay, that will be our 12th lecture, and I have taken one extra class also that will be going to held on 15th October, 4 to 6 p.m. Okay, so please join that session also. Okay, all set. Yes. So let's directly go to our assignment. So this is our assignment. So assignment number 9. Today we are going to solve our assignment number 9. So this is first question number 1. Okay, which is it's saying that the question says that in BeH2, two possible SaLCS of hydrogen atoms, 1s orbital are these two, and the function is also given. The correct statement among the following is, okay, so it is like so here I am considering, so this BE, let's is have like, which orbital it will going to participate in bonding, it is 2s, and 1s orbital is of hydrogen. Okay, so it's like sigma 1s equal to like plus, and this also going to be what is this? This is minus. Okay, so if your if your if beryllium, this is having positive 2s, so it will form bonding orbital, right? If this is the situation, then if let's say this plus and plus, and your beryllium is minus Be, okay, so this will be your anti-bonding molecular orbital. Okay, So according to that, option 1 is saying that sigma phi 1 can form bonding this as well as anti-bonding molecular orbital with 2s orbital of Be. So I think this is, I have what I taken plus. This should be plus. Okay, now it is fine. So this is bonding, this is bonding, this is anti-bonding. So if you look closely, that I have taken function, this function. So that is why it is plus and plus, because here it is plus and plus. Okay, so plus and plus. So it can. What are the two situations left? If we introduce this Be 2s orbital, so it can be positive or can be negative. Fine. So if it is positive, it will form the bonding molecular orbital. If this is minus, then it will form the anti-bonding molecular. Then it will form the anti-bonding molecular orbital. Okay. So I think option one I can see that it is correct. Psi 1 can form bonding as well as anti-bonding molecular orbital with 2s of Be. So this is the situation you can think of. So option 1 according to me is correct. Okay, let's check the answer. What is the answer of this question according to the NPTEL team? Okay, answer is A. So I think we are correct. Fine. In extension to that, let's say take another slide. In the previous question, in this question only, if they ask what are the symmetries, Symmet- symmetries. Actually today I don't have pen, I lost somewhere, so that is why my handwriting is not uh, good today. So but I will try to make it as good as possible so you guys can understand. So in addition to that, uh, so question we have already solved, but I am just extending little bit. So I am asking the symmetry of psi 1 and psi 2 R of this question. So let's say like what will be the symmetry of these two? psi1, phi1s, phi1s, and what was there? Phi1s, minus minus. Psi2 is phi1s minus phi1s. This is of A atom, B atom, A atom, B atom. So let's say I'm considering this situation in which this HA and HB are here. Okay, these two both are positive lobes. These and so what will be the, okay, if this is your molecule, let's say, so what will be your point group? It will be D infinite H, because it is linear molecule. Okay, you have center of inversion here in between. So for D infinite H, what will be your point group? The symmetry element of this point group: E, C infinite, sigma V, I, inf oh, this should be infinite C2. Okay. So if you try to find out the reducible representation for this, so what will be the E will be like, no, E will be 2, because it is not changing any of the atom. And for C infinite, this is a C infinite. So it will also not going to, all the atoms, both the atoms will remain same. Sigma V also, character will be 2. For I, they will interchange. I will be here, so they will interchange. The character will be 0. So for S infinite, and for C2, C2 will be here it should be also 0. Fine. So D infinite H character table for plus plus, what will be the this, what will be your Mulkan symbol? Okay, and if this and this, then what will be your Mulkan symbol? Today is very difficult to write actually, because I am using my hand. Let's say this is sigma 1, this is psi 1, psi 2. This is anti-symmetric. For anti-symmetric, why it is anti-symmetric? It is anti-symmetric because if you apply I, they will interchange. Okay, so we need character table d infinite h. D infinite h. D, no, not this one. D infinite h. I am not able to h. I got the table, but okay. D infinite h. Okay. Copy means not able to paste it here. Allow. Fine. Oh, everything I have written is gone in. Anyway, so for that I have written plus for z and plus minus sigma u this. Okay. Is lost. Okay, I'm leaving it here because there is too much calculation and also it is difficult for me to write. Anyway, I have solved this question. Anyway, we have got the answer of this question, question 1. Okay. Okay, moving to question number 2. Localized MO picture of methane is not tenable because so we need to find the correct answer. So methane CH4, so 1s 2s 2p, 3 bond length same and one is different. One is different. So these are sigma. These are sigma, sigma, sigma bonds, and p orbital will be like this. So localized MO picture of methane is not tenable because of carbon atom does not have atomic orbitals at 105 degree to each other. Of course, we will not have. It will not have, as I have drawn this uh, structure and the orbitals overlapping of the methane. So this is all. This is your answer. Also, uh, out of these tetrahedral, yes, of course, point group of methane is tetrahedral. Okay, character table does not have four-dimensional representation. So for that, yes, this is also correct, because if you remember, it doesn't have character table of tetrahedral. Tetrahedral character table. Okay. So this is the character table. Copy image. As you can see, it has maximum dimension of 3. Oh, dimension of 3. So character table, option D is saying character table, a tetrahedral character table does not have four-dimensional representation. Yes, it is also true. As you can see, tetrahedral character table I have shown you. So here will be the dimension for how we are, because these are localized. This 3 4, all the bonds are localized, means they are degenerated. Okay, so these, their symbol should be A1 and T2, which is equal to A plus 3, I mean 1 plus 3, so it will giving you the 4. This is your 4 bonds. They are degenerated. So, so these two are correct. Keeping in mind that we are right. Option A and D. Okay, moving to question number 3. Uh, Question number 3. Linear combination of atomic orbitals of 4 atoms in methane have the following symmetries. So that I have already told you that symmetry it is a symmetry A1 plus C2 T2. Let's solve it. H H H H H A H B H C H D 1s 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 1s. Handwriting is too bad. Okay. Positive, negative. So combination of these 4 psi 1 1s1, this is one condition, 1s and 1st. This is one condition when let's see you I have do we have here animation, transition, design, theme, sort. No, we are not. Let's say this is the condition. Here one H atom is present at this position, and at this position. In that situation, this is the condition. Bonding orbital, anti-bonding orbital. So this is positive, negative I have written. Let's say here these are all of them were positive. Next situation is that let's say this is also possible. This is also possible. In that scenario, what will happen? Phi 2 equal to 1s A plus 1s B minus 1s C minus 1s D. Similarly, phi 3 will be 1s A, 1s B, okay, sure, plus 1s C minus 1s minus 1s D, 1s D. So, as we already know, 3, we have wrote 3 condition only. So, this is total symmetric. Which condition? This condition is this condition is totally symmetric. Totally symmetric. Condition is totally symmetric. As you can see also from character table, because there the question is saying have for linear atomic orbitals, linear combination of atomic orbitals of 4 atoms in methane having the following symmetry. So it has the point group of tetrahedral. So this is the character table. So in which you can see this all are 1 1 1. This is fully symmetric. Fully symmetric. This this is the this is one situation. And also we have phi 1, phi 2, phi 3, also going to have phi 4. Phi 4, 1s A minus 1s B minus 1s C plus 1s D. So if you try to find out, have the following symmetry. So symmetry, as I have already told in the previous question, symmetry of Salk will be A1 plus T2. So C2S is A1 and C2PXYZ will be T2. A1 I have already told, right? This is totally symmetric, which is matching to this A1. This A1. That is why this symmetry is A1 here, and combination of all these atomic orbital we got other three also, other than the phi 1, other than the phi 1, we have phi 2 and phi 3, phi 4. So these three are for T2. T2 we already have seen that the degeneracy is 3. So that is also we are getting 3. Phi 2, uh, phi 2, phi 3 and phi 4. This is for Px by NZ. So these are the symmetries. So if you find out, if you try to, so how many atomic orbitals will be there? Molecular orbitals, 8. 4 will be bonding, 4 will be anti-bonding, molecular orbitals. So what will be the answer? I already told This should be your this should be your answer. Option B. Fine. Okay, moving. Oh, okay. Moving to the next question. A a trigonal bipyramidal complex. This is the TBP. TBP. The equatorial bonds. So sigma, let's say 1, sigma 2, sigma 3 involve orbitals of symmetry. So tell me, what is the point group of this TBP? Okay, Patlekha, Shivam, try to tell what will be the point group of TBP complex molecule. C2V. No, C2V is not correct. C2V is not correct. Then it should be C. Just imagine, no. Uh, that TBP, trigonal bipyramidal. So trigonal is in the plane. Is in the plane. In bipyramidal, both and other two bonds which are perpendicular to this your trigonal plane, it is above the plane and below the plane. TBP, symmetry. Maybe it will be more clear if I draw it like, let's say, PT, CL, 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 CL. Now try to find out what will be the point group of TBP. Perfect. Point group of this is D3H. So to solve this, we need corrector table. D3H. So here bases are your equatorial bonds. Okay. So bases are equatorial bonds. So according to our notation, it is sigma 1, sigma 2 and sigma 3. So tell me what is the order of this point group order? 12, yes. It is 12. So now let's draw like this. Sigma 1, sigma 2, sigma 3. Now try to draw this character of these equatorial bonds. E 2C3, 3C2, sigma H, 2S3, 3 sigma V, sigma V. Okay, now it's your turn to tell me that now your basis. I have already told that what is your basis. Your basis are these equatorial bonds, sigma 1 to 3. Only those equatorial bond I have drawn here. Okay, so according to that, tell me what will be the character if you apply, what will be the character if you apply identity operation. Please show the character table. No, you don't need character table. This is your reducible representation. So how many number of in the case of atom are not changing? In our case, it is bonds. So if we apply the symmetry element, this identity element, identity operation, your this all the bonds remain as it is. So character will be 3. This is irreducible representation of E equatorial bonds. So bonds are not going to change. Yes. What about C3? If you apply C3 operation, then what will happen? I mean, what will be the character? Zero. Perfect. What about C2? How 1, yes. Sigma h. 4. There are only 3 equatorial bonds. Your bases are equatorial bond, not the atoms. 3. S3. S3. No. S3, you have to apply C3. Then, then you have to apply sigma, right? So, as you apply C3, all the bonds will going to change their position. So what will be the correct term then? 0. And for sigma b, I think you are making the same mistake. This stage, you, I think in your head you are always considering the atoms. Your bases are bonds. So let's say this is your plane, which will contain this sigma one bond only. So like that you have 3 sigma v's, which means only one bond will not change. Yes. So your character will be 1. Now according to that your GOT, you have that great orthogonality theorem. You have that uh, formula AI 1 by H in brackets summation irreducible representation and xi for. Okay, so according to that, this formula you need to find out first what was a1 dash. So irreducible representation for, I mean how much the contribution of a1 dash, a1 dash, yes, in the irreducible representation. This is reducible representation in the irreducible representation. So it will be 1 by 12, as we have already know that the character of this is 12. The order of the point group is 12. Okay, then Am I audible now? My screen is visible? Yes. Okay, fine. So you have to multiply 3 1 1 plus 1 3 1 plus 3 1 and 1, like that. If you solve, you will get 12 by 12 equal to 1. So in this table we have how many symmetry these orbital, these symmetry elements? 6. Not the elements, sorry, these symbols. 6. So we have to do this for 6 times for all of them. But let's say A1, A2 dash, 1 by 12, 1 plus 3 plus 3 plus 1, 3 minus 1, and so on and so forth. You'll get 0. For O3 A E dash equal to 1, A 2 dash double dash equal to 0, A2 double dash equal to 0, A double dash is equal to 0. So T, this irreducible, you will get E dash, what else? All of them are 0 here. This is one A1, A1 dash plus A1 dash. So this should be your answer. This I have not solved fully because you know how to solve it. Okay. So A1 dash E dash, A1 dash E dash. So this is your answer. A is your answer. Yes. So I think we have solved it correct. Okay, moving to question number 5. For C2H4. Shown in figure above. Okay, I don't see any figure anyway. So this will be CHHHH. So this is ethene, right? Tell me what is the point group of this molecule. Then we will solve. D2H, perfect. So we need character table of D2H point group. Okay. So here for C2H4 shown in figure above, in this figure a projection operator operates on, okay, so this is misprinted, remove this sigma first, sigma, 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 sigma. So a projection operator on sigma 2 yields sigma 1 plus sigma 2 minus sigma 3 minus sigma 4. The projection operator is of symmetry species. So on which symmetry species the projection operator applies? On sigma 2 bond, which yields this sigma 1 plus sigma 2 minus sigma 3 and minus sigma 4. So this is the question. So they are asking for the symmetry species on which this is applied. So let's consider this is your x, this is your y, z you already know it is above the plane. Okay. So for E, so again draw this C2. We have C2, 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 then I sigma, sigma, sigma. So this is x, this is y, z, this is xy, this is xz, this is yz. Fine. So after applying the E-symmetry operation, what will be the character? So here your here was the sigma means bond. Do not consider atom. Sigma means bond. So there the projection operator operates on sigma 2 means it is asking for your bond, CH bond. Let's say this is sigma 1, this is sigma 2, this is sigma 3, this is sigma 4. So now tell me what will be the reducible representation or reducible characters for these symmetry operations. So for E, tell me what will be the character. No, only we are talking about CH bonds. 4. Next, for C2X, 0. C2Y, 0. C2Z, 0 I 0 sigma xy. For sigma yz, sigma xz. No, this is plane xz. So plane is not, so xy, in the xy plane you are, this molecule is planar and the plane is xy plane. So now if the now other than xy plane, any plane is perpendicular to the molecular plane, which will going to reflect all the bonds. So the this will be like this. Consider this in the x direction, and this is coming out. So all the bonds will reflect like that. In the by next yz will be this. These will go like this. Inter okay, interchange their position. So this is 0 0. Perfect. Now we have to find the irreducible representation. So it is a very lengthy process, but I have already solved, which you already know how to solve. So, how to find out these reducible representation of this molecule? It will come out to be Az plus V1Z plus V2U plus V3U out of all these. Now the projection operator on Az of Az on sigma 2 bond, and projection operator of V1Z on sigma 2, projection operator of V2 on sigma 2, projection operator of V3U on sigma 2. This is what we have to find out. So by applying this projection operator on sigma 2, whatever the irreducible representation, these symmetry these symmetry species we got, by applying projection operator of this symmetry operation, we will get the these, I mean which symmetry operation the projection operator of this symmetry operator, this symmetry species applied on sigma 2 will give you this sigma 1 plus sigma 2 minus sigma 3 minus sigma 4. So nothing can be done. We have to check one by one. So what is the requirement? What is the requirement? Requirement is sigma 1 plus sigma 2 minus sigma 3 minus sigma 4. These are very lengthy question actually. So next we have to find out this E C2Z C2Y C2X I sigma XY sigma ZX sigma YZ of V3U. V3U. No, this is okay. We have already found this. Already got this representation. This reduce one. So now it's time to just solve. So for projection P V3U, let's say I'm solving for the last one sigma 2. So it will be like 1 multiplied by, because the character was 1. So what will happen? This, let's say I'm drawing this again. H sigma 1, let's say 2, 3 and 4. So by applying E, what will happen to sigma 2? Nothing will happen to sigma 2. So sigma 2 will remain sigma 2. Then minus 1. This minus 1 is coming because of, let's say, this sigma z, because of this minus 1. These we are multiplying with these characters. And here all of them, these all are 1. See, 1 1 1 1 1. So we don't have to consider, I mean multiply, because it will not going to change. Next, for minus 1 z, along the z, what is happening? This is your z above the axis. Sigma 2 is becoming, sigma 2 is becoming along the z. This is your z along the z. This will, this sigma 2 will go there. So this will become sigma 4. and so on for so forth. For all the symmetry operation, if you solve, at the end you will end up getting with for sigma 2 it will be twice of sigma 1 sigma 2 minus sigma 3 minus sigma 4. I think this is what the question is asking. 1 2 minus 3 minus 4. 1 2. Okay, this is only. So by applying the projection operator of this symmetry element on sigma 2, you are getting the answer question. So this is your answer. Similarly, 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 this for projection operator of AZ, this AZ sigma 2 will be sigma 1, sigma 2, sigma 3 plus sigma 4. Projection operator of V1Z is equal to sigma 2 equal to sigma 1 minus sigma 2 plus sigma 3 minus sigma 4. We have already got the answer, but I'm just giving you the, if you solve it by yourself, what you will get. Sigma 1 minus sigma 2 minus sigma 3 plus sigma 4. Answer you have already got. BU3, this is B3U. So answer is D. Answer is D. Okay, you got it right. I'm just giving you the hint and solve. Yes, okay, fine. Yeah, I'm giving you the hint. Hint and also solving little bit, but not fully solving. Anyway, coming to our next question. Next question is delocalized MO picture of methane. Delocalized. We have already solved this question. What are the symmetry we got? See, A1 and T2 for methane. A1 is singly degenerate, and this T2 is, oh, I have, this is T2, not this one, this one, T2. So this is T2, triply degenerate. But question is saying delocalized means all are degenerate. For methane case, okay, let's say this is sigma 1, sigma 2, sigma 3, sigma 4, all are degenerate. We have already this one, this is there, 3 degenerate orbitals there. So first option is that the delocalized MO picture of methane is in agreement with both photoelectron spectrum and rotational Raman spectrum. So the delocalized MO picture of the methane is in agreement with both. Yes, it is in agreement with both photoelectron spectrum and rotational Raman spectrum. So this is your answer. Because this is delocalized. Okay, till now we have solved uh, assignment 9. Now in assignment 10 also we have 6 questions. So let's start from the last. So the question is saying, for the same character table of question 5, for 5, if the initial and final stage belongs to A1 and B1, irreducible representation respectively, the allowed electronic transition from A1 to B1 is. So here the checking out the character table of C2B. So they are asking, question is saying for C2B point group, the reducible representation correspond to 3 translation degree of freedom. Anyway, C2B, we need to consider the character table of C2B. C2B. So for this we need only the cross multiplication of A1 and B1. So A1 is 1 1 1 1 and V1 is 1 minus 1 1 minus 1. Anyway, after the after this multiplication, what you will get? 1 minus 1 1 minus 1. This is 1, which is B1 only, right? Is it okay? Yes. So we are getting V1, and V1 is, if you are able to see, or let me zoom it out little, zoom in little bit. Now you can see. So V1, this B1 is having X. Okay, along the X. So it is possible when you the allowed transition from A to 1 is X polarized. This this type of question we have solved in previous assignments also, where they have in the question specifically mentioned that using Z polarized light we got this, and that the transition is this, then you find out something. So here the transition, the this function is x, linear function x. So along this, so the answer should be x polarized light along the, if you use the x polarized light. Okay, is it okay? Yes, sir. Okay, next question is, so same character table I need to, anyway character table is there only, here only. Check out the character table of C2B point group. The reducible representation reducible correspond to three translational degrees of freedom. Now we have to again find out this E C2 sigma xy, what is that, sigma yz, irreducible translation. So basically 3 degrees. Bases are x, y, z. Perfect. Bases are x, y, z. They are asking about the translation degree of freedom, tau r. Okay, so by applying the symmetry operation E, what will be the character? Or you can, for Z is A1. So for, let's say this is Z. For Z, what are the character? 1 1 1 1. For X, what are the character? 1 minus 1 1 minus 1. For Y, what are the characters? 1 minus 1 minus 1 1. Fine. These are your translational. Today I don't have pen, so that is why handwriting is too bad. Anyway, so by summing all of them, these translational degrees of freedom, what you will get? 3, next minus 1, next plus 1, next plus 1. Is it okay? So these are your reducible representation. I think we got the answer, right? The reducible representation corresponding to 3 tower. That's what they have asked. The question is asking. So 3 minus B option, right? Yeah, answer is D. Did you get it? Fine. Okay, moving to question number 4. Of the following, the point which is not an advantage of using incomplete projection operator over complete projection operator is. So first, you need to know little bit about this. So basically, it is the, let's say, the 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 projection operator, incomplete projection operator means, let's say this is the transformation matrix. If it is complete transformation matrix, this complete projection operator, then all for all, let's say the point group is D6H. So for that, the symmetry element, let's say E, C6, S3, C3, C2, sigma H, sigma V, and so on and so forth. For all of them, we have symmetry of these uh, symmetry transformation matrix. So for all of them, if it is if, let's say, order is high, then for all the operation you have to solve to find out this reducible representation and other thing. But by using the incomplete project operation means you are only using the diagonal elements, which is trash. I have initially also told you this trash. So using this, the process is little bit simpler. So the question is, over the following, of the following, the point is a point which is not an advantage of using incomplete operator over the complete operator. So option, let's say, let's start from B. There is no need to work with the entire transformation matrix, that I have already said. So this option is correct. Character table can be used directly to work out the operation. Of course, the process is less tedious, of course, because you don't have to do all the math now. So basically, these are advantage. They are asking about the not the advantage. So resultant linear combination of atoms are automatically normalized. Okay, but this is not an advantage anyway. So on these are advantage. So they are asking what is not, which is not an advantage. So option A, this is not an advantage. Incomplete. This incomplete. I have to let me the incomplete. This projection operator is summation of diagonal elements equal to trash or character. That is why this can be used this your character table directly to work out the operation. Let's say this is the C2 transformation matrix, 1 minus 1 1 0 0 0 0 0 0. So if you add all of them, this is minus. So what you get is minus plus 1. Fine. Is it okay? Fine. Okay. Next question is for C2H4. For C2H4, shown in figure have a weak projection operator of sigma 1 to yield this is the projection operation is of symmetry species. This type of question just now we have did, right? Anyway, we will solve. So let's say sigma means sigma 1, sigma 2, sigma 3, sigma 4. Now these are your axes, x, y, and now try to find out E. What will be the point group? Tell me. Point group. What will be the point group of C2H4? Yes, D2H. D2H. So we need character table D2H. Sigma 2Z, sigma C2y, C2x, I, sigma xy, sigma zx, sigma yz. Now tau sigma, the reducer representation for sigma 1. Tell me what will be the characters. Four. Next, for C to Z, zero. For C to Y, 0. For C to X, for I, for sigma XY, for sigma XY. Four. For ZX, 0. For sigma YZ, 0. Okay. So final. After solving, you know how to solve. For D2H, okay, the irreducible representation you will get AZ plus V1Z plus V2U plus V3U. So fine. You know how to solve these. Now apply the projection operator. on sigma 1. AZ, I think for AZ, no, for AZ D2H, yeah. For AZ you can see the character here. All of them are 1 1 1 1, right? For all the operation the character is 1 for AZ element. Symmetry of for AZ symmetry species. And also here all the operations are multiplied, the coefficient of the operation is of all the operations are 1. Okay, so here for this what will happen? Here I again should write 1h sigma 1 2 3 sigma 4 will be 1 for E plus 1 multiplied by C2 4 and so on so forth for all of the symmetry elements. This is how you can solve. So okay, what will happen? Tell me. For E, the sigma 1 will remain sigma 1 anyway. This is sigma z, let's say. Sigma 2z will become sigma 2z. This I have already told that this x and y is here and z is above the plane. So you already know the coordinates. So now what will happen by applying the C to Z? This sigma 1 will change the position with sigma 4. Right? Similarly, 1 multiplied by this C2, let's say C2y. What will happen to C2y? This is your y direction. Will change to 3. And then so on and so forth. You can solve. In the end, you will get projection operator applying on AZ, or projection operator of AZ applying on sigma 1. In the end, you will get sigma 1 plus sigma 2 plus sigma 3 sigma 4. Fine. I think this time we got lucky. This time we got lucky because the projection operator on sigma 1 of AG, we have solved for AG, projection operator of AG on sigma 1. We got the answer sigma 1 plus sigma 2 plus sigma 3 plus sigma 4 yields to, the question asking for yields to the same answer which we got, sigma 1 plus sigma 2 plus sigma 3 plus sigma 4. The projection operator age of symmetry species, now we know, easy. So this is how you solve. You can also solve for other symmetry operator species. Okay. So answer is 1. A. A is the answer, yes. Till now, did you understood this? How we are writing this sigma 1 is remaining sigma 1 or sigma 3, sigma 4 here by applying this projection operator. Got it. Fine. Because if you apply this C2 by operation, then where this bond will go, this bond where it will go after applying. If it is going to sigma 4, then you have to write here sigma 4. If it is going to sigma 3, you write sigma 3, like that. Then you solve it. Okay, this time we got lucky. Answer is A for third question. Okay, only two questions left for this assignment. Okay, the next question is, of the following, the statement is the statements pertaining to use of subgroup rather than the full group of the complicated calculation. The correct one is, the complex characters are necessarily avoided, the smaller number of projection operator are required. Of course, that's what we have discussed in one of the question, right? This incomplete projection operator, if you are applying, which means you don't have to do the calculation for all the symmetry operation for the full transformation matrix. So smaller number of projection operators are required. So here the statement pertaining the use of the subgroup rather than the full group. Complicated calculation. The correct one is this, the smaller number of projection operators are required. Answer should be B. Answer should be B. Yes, answer is B. So what I'm trying to say is that let's say it is this, let's say octahedral. What is the order of octahedral point group? No, 48. So the subgroup of octahedral is D4H, C4V, like that. So what is the order of D4H? Not 24. You have to apply this 4 into 4. 4 is n. So total is 16 order. So, and for if the point group is starting from C, then 2 into n, 4. It will be 8. So what will be the order of D3H? Tell me. Yes. It will be 4 into 3. Okay. So full group here is complete group. Subgroup is incomplete. So like if the point group is octahedral, then if you want to find out the projection operator applying on some bond, then the question is asking what we yield, like the previous question. So for all you have to solve for all these 48 symmetry operations for one symmetry operation. For one symmetry species, you have to solve uh, look for all these 48 symmetry operations, right? Then the chances of uh, calculation mistake is high. Also, it is very time consuming. So that is why what we do, we just uh, find the subgroup of that point group and solve it. So and then we extend it to find the correct answer. So so that is why the smaller number of projection operator are required. So that should be the correct answer. Did you get it? I mean, what I'm trying to say, you have any? Yes, finally. Got it. Okay. Okay. Next question is, this is our last question also. Tell me. So this figure is in the square planar complex. Figure 1, this minus this forms are the basis of for a two-dimensional representation along with. So basically, sigma 1 minus sigma 3 forms the basis. The question is saying sigma 1 minus sigma 3 is the basis for the two-dimensional representation along with. So basically, they are asking other basis pair along with sigma 1 minus sigma 3. Fine. So, so by elimination, this cannot be possible because they are asking for two-dimensional. Right? This cannot be possible. Is it okay? Okay. So tell me, what is the point group of this molecule? This is curve-planar molecule. What is the point group? consider this, no? Cl, 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 Cl. Not C2V. Not C2V. Square planar. It is written square planar complex. Square planar. Plane. D4H. Yes. Point group will be D4H. So we need D4H, the correct table of D4H. So this time, if you look closely, the bases are not bonds. I mean, not a single bond, not atomic orbitals. This time, bases are these. No, no, no. One second, one second. No, no. Sorry, sorry. The bases are bonds only. Bases are bonds only. So along, okay. For D4H, I am writing these E, the symmetry operation E, C4V, C2Z, C2 is perpendicular to C2 double dash to S4. This is S4 I sigma H sigma V sigma D tau sulk. Now tell me, this is, let's say, sigma 1, sigma 2, sigma 3, sigma 4. So by applying E operation on this square planar complex, what will, considering the bases are your bonds, what will be the character after applying E operation? Any answer? So you're saying 4. Yes, 4. For C4, what will be the character? 0. For C2, 0, and for C2 perpendicular, so for C2 C2 is like C4 is perpendicular, C2 perpendicular is perpendicular to your principal axis, this C4. So let's say this is if this is your C2, then it is 2, other are 0. Now for S4, 0. For I, 0. For sigma H, for sigma H, 4. And for sigma B, no. It is square planar. No, sigma V means it is containing your uh, this principal axis of rotation. No, not sigma D, sigma V. 2, yes. And sigma D, 0, yes. So till now we have solved, like, got the reducible representation, right? So tau, oh, solves A1Z. What you get at the end, I'm writing that. You know how to solve it. Use that or great orthogonality theorem formula. Find out the contribution of each of the symmetry species. Then you can find out this irreducible representation. Okay. EU. Now apply the projection operator of A1Z on sigma 1. You will get, you also know how to solve this. I have told sigma 4. You'll get this. Right? You know how to solve this projection operator. I have already told. Projection operator of V1U sigma 1 is equal to, yes, sigma minus 1 sigma 2 plus sigma 3 minus sigma 4. If you apply projection operator of E U sigma 1, you will get sigma 1 minus sigma 3. So basically a irreducible representation has 3 symmetry species, and we applied projection operator of all these 3 species on sigma 1. Why we apply on sigma 1? Oh, okay, because all of them are these degenerate. I mean, the bonds are equivalent, so there is no problem. We can apply to sigma 2, sigma 3, or sigma 4. You'll get the same answer, anyways. So this, but this, if you look closely, this is one dimensional. This is one dimensional, but this is two dimensional, right? So it will have two sulks. So we know, and the question is asking for sigma minus sigma 1 minus sigma 3 form the basis of a two-dimensional representation, which means that these above two, A1G and V1U, these are not possible. But the traditional method we use to find out this basis by applying the projection operator on any bond, we are still not got any this basis which is two dimensional other than this sigma 1 minus sigma 3, right? So how to find it? This is very simple. How to find it, right? So let's say here we have C4, C2. So what? Let's consider this. Let's say C2. If the bases are X and Y, so after applying, X will interchange to Y will interchange to X. That's what happened to C, right? So so for this, what will happen? For sigma 1 minus sigma 3, one of the bases of 2D representation. We have already know this sigma 1, sigma 2, sigma 3, sigma 4. Now let's try operation on this basis. What you get? The same base, sigma 2, sigma 1 minus sigma 3. If you apply the next symmetry element, symmetry operation, what is that? C4. C4 on sigma 1 minus sigma 3. Tell me what you get, what you got, what you will get. So this sigma 1 will go there, will become sigma 2. What happened to the sigma 3? It will go there, minus sigma 4. So this basis will come. Similarly, if you solve for for all the operations, C2 perpendicular, C2 double dash S4, I, sigma H, sigma V, sigma D, you will ultimately get you'll got this only, sigma 2 minus sigma 4. So is this matching with your answer? So that this can be the possibility, one of the basis of 2D representation other than sigma 1 minus sigma 3. So what is sigma 2 minus sigma 4? Sigma 2 minus sigma 4. Yeah, so option C I am able to see. This is correct. Option C is correct. Fine. Similarly, you have to solve for all of them. You will get this sigma 2 minus sigma 4 or sigma 1 minus sigma 3 or 0. I mean nothing. So this is your answer. Fine. Okay. So I think to this session is almost finished. We have solve assignment 9 and 10. In the next class, okay, next class is tomorrow only because I will be traveling on 12. So I will not be able, I will not take class on 12. So instead of 12, I will be going to take class tomorrow, same time, 4 to 6 p.m. And I have already taken one extra class which is going to happen on 15 October, 4 to 6 p.m. same time. Okay, so join tomorrow for the class at the same time, 4 to 6 p.m. Okay, see you tomorrow then. Okay, bye. I'm ending the session now.